Okay, I think we're good to get started today. Thank you for coming out. My name is Nick Winovich. I'm in the Department of Mathematics. I've been working with machine learning and TensorFlow for the past 3 years, and I've also had an opportunity to teach undergraduates through the NSF SURF program about TensorFlow and had the opportunity of going through the learning process multiple times. So I thought I would put together basically a presentation on how to get started with TensorFlow. And in particular, this will be directed at graduate students. I'm not going to walk through kind of the very basics, hello world style programming, but I really want to highlight some of the key points that were important and that I missed the first time that I went through the process of learning TensorFlow. So in today's workshop, we will first cover an introduction and background to the core concepts behind TensorFlow. We'll also discuss some of the best practices as described by the TensorFlow API. And then in the second half of this talk, we will go through some of the more advanced features and the new types of tools that TensorFlow has implemented in the most recent version. So to begin, I want to just give a very brief summary of what TensorFlow is. It is a library for numeric computations, primarily for deep learning and neural networks. The key behind TensorFlow is that it's designed for high performance and scalable models. So it's really the kind of industry standard for working with large data sets and computationally expensive processes. So two kind of great resources for getting started with TensorFlow are the API and the YouTube channel. The YouTube channel has just been recently introduced, and in particular, there's the developer summits, which highlight basically the future directions and where the TensorFlow code is kind of being directed for the future releases. And it's also open source, so if you have any technical questions, if you want to know what order a certain layer places its operations in, you can always consult the source code directly, which is available on GitHub. To install TensorFlow, there's already a pretty great overview on the TensorFlow API website. But in most cases for Linux, and if you have the pip package manager installed on Windows or Mac, you can just install it by pip install upgrade, and then a URL for the Python version. So in this case, I have a 3.5, 3.7. 3.5 or 2.7, and those are available along with more complete instructions, as I mentioned, on tensorflow.org/install. So I won't cover that too much, but if you want to go ahead and give that a shot and install that during the break that we'll have halfway through today's talk, then I'd be happy to help troubleshoot if you have any questions. One point that I would like to make is that it may be worth installing TensorFlow in a virtual environment. So Python has virtual environments which isolate the libraries such as TensorFlow and its dependencies from your system's installation of Python. So for Linux, for example, Python may be used to install some of the system programs, and if you kind of mess around with the dependencies, you can run into a lot of errors. So it's just something worth noting. It's fairly straightforward. You make a virtual environment, and then that can protect basically your system's installation from the TensorFlow environment. So I want to jump right in to the core concepts that TensorFlow works with. And the first concept, as the name suggests, is that of a tensor. A tensor is in many ways a multidimensional array. We treat them a little bit differently, as we'll see throughout the course of this talk. And in particular, the way that TensorFlow is structured, a tensor is really a symbolic handle to the output of an operation. So it doesn't actually store values, which can be at times a little bit confusing, and we'll talk about how to interpret TensorFlow code. But what it does take account of is the data type and the size of that output. So if you're thinking maybe in like a C programming language, it needs to know the data type and the size so that it can basically allocate memory. And the same is true of a tensor. It knows that information, but it does not necessarily know the value that it contains, the actual numbers. So that will be accessed in a different way, but we'll see that's relatively straightforward. So as I mentioned, tensors are symbolic handles to the outputs of operations. So what is an operation? Well, basically it is what we want the code to do, the computations, the calculations within a graph or this kind of structured code. So we specify computations basically between the inputs and outputs. Do we want to add them? Do we want to multiply them? Or what combination of operations do we want to basically perform to transform our data? And these can also be used to produce tensors. So if we want to initialize a value, you can just generate a random tensor or a constant tensor. And again, that will generate a link which we can evaluate later. These are also key in machine learning for defining our optimization algorithms. So in the algorithm, we want to perform some computation, some update, and that's accomplished by running operations. So putting all of the tensors and operations together, we have an organized system or network of computations. And this concept is encapsulated in the notion of a TensorFlow graph. So this is a computational graph which shows us what the data flow or the connectivity patterns of the computations are within our basically network or our model. In particular, they specify the dependencies or the connections between different computations. So we know if we want to compute B, and that requires a calculation of A first, that we should first compute A and then proceed to B. And this is important because, as we'll see, it allows us to kind of strip down the model and only evaluate what is necessary at any given time. So as a simple first look at the code, we see we import the TensorFlow library as TF typically is the standard way to import it. And we want to define constants for this particular example. So this is an operation technically which generates a constant tensor. Its value will be 1. We tell it that it's a single precision float, and we assign it a name so that we can access it later if we want to save the model. So we'll assign these to Python variables A and B, and then we want to compute the sum. So we'll use the tf.add. We'll add A to B, and we'll give that a name as well. If we stop right here and we print that symbolic tensor, what we'll see is a shape, which is empty, which just means a scalar. It has no dimensions, and a data type, the float. So it knows the shape, it knows the float, but notice it does not know the value. We do not get 3 out of this. Instead, we get its name, sum:0. And this can be visualized in graphical form in using TensorBoard, which we'll discuss in the second half of the talk, as 2 input nodes, these symbolic tensors A and B, being passed as inputs in this directed graph to the sum operation, and an output of S is produced. So this is kind of the way we think of these graphs, and obviously there's more interesting examples as the network gets larger. But that's the basic idea, is these show the connectivity between different operations and tensors in the graph. So as I mentioned, the value 3 was not actually computed. We already had written all of that code, but we still didn't figure out what the sum actually is, or what the result is in that case. To do that, we use a session, a TensorFlow session, to run or execute the code. So first we build the graph, basically lays out the data flow or the computations that we intend to make, and then we execute that in a separate TensorFlow session. So these are the 2 fundamental concepts, the graph and the session. And as I pointed out earlier, so we'll give the session a list of fetches, just things to evaluate, and TensorFlow will automatically determine the subgraph which operations it needs to compute in order to produce that list of fetches, those specific tensors that you ask for. So it will not just run all of the code, as it may if you just write this naively in Python. It will execute what is necessary to produce that specific list of computations. So for example, we may ask it to compute sum. In the previous example, we had gotten all the way up to print s. We saw it gave us the name, but it did not give us a value. So what we do is we open up a TensorFlow session. So this is just a way to automatically close the session after we exit this code block. So with tf.session as sesh, we just assign it the name sesh. And we execute the graph by running session.run. Session.run, in some cases, you'll have a list here. We just have one tensor that we want to evaluate, s, which is the sum. We'll store that as a result, the Python variable result. And when we print that, we do, in fact, get the value 3 that we anticipated in the float format. So the first part is effectively constructing our graph. As we saw, you can visualize that as a directed graph with nodes corresponding to operations. And second, we initialize a session and execute the graph within that session in that run context.
I have a question.
Yes?
Like instead of using tf.add, you would have used like a plus b. Will it create a different graph?
It will create the same graph for most NumPy operations, but it's best to, in my experience, I started much earlier and there was some bugs. I believe they've ironed that out. But to be safe, I would recommend always using TF operations. They have almost everything, and one of the things that is important is that it keeps track of the gradients. So it will register the gradients of these operations, and you can be sure that those gradients will be computed correctly if you use the tf.add. I believe they automatically catch, if you just use a plus symbol or NumPy, they catch most of those. But to be safe, I would recommend using tf.add. Yeah. So one of the things that I glossed over earlier was the name. I had named the operation sum. And when I printed the value, it said sum:0. And I didn't know what this meant for probably the first year that I was working with it. I just thought it was always added for some reason. But the reason that it adds that :0 is that you're not actually referring to the operation anymore. If I look here in my slides, so this sum:0, this is actually the symbolic tensor produced by the operation sum. So these suffixes are added to indicate the outputs, starting with the first Python index of 0, of the operation. So sum:0 is the first output of that operation. And this will be helpful if you ever need to access points in your graph after you've saved them, for example. So a kind of more complicated example, but nothing is too important to understand other than this is one of the few things that makes multiple tensors or produces multiple tensors. So if I compute a singular value decomposition of the identity matrix, I'll get 3 values, and we see those names are SVD 0, 1, and 2. So there's just the number, the value produced, because when we save these models, the Python variables s, u, and v are irrelevant. They won't be accessible after we store this, so we need to have direct names or handles to call so that we can still retrieve that from the graph. And when we execute again, those values are actually computed. So in this case, it's just the identity. So we get basically all ones, the singular values and the singular vectors. And the graph for this, as you may expect, we take the identity. So there's the operation I, which produces an identity matrix. It knows the shape. It also knows the data type. It's just hidden in the graph. It goes to the SVD operation and branches out into 3 different outputs. So just another example of the TensorFlow graph. Another word on Python variables is the name scope, or the variable scope. In terms of writing your code, it's a very easy mistake to make. So I say, why not just use s instead of sval? If I go back here, I have s here, sval, I want the value. Well, in this case, it may not be important, but if we're ever looping, or if we want to use this symbolic tensor again, this S, we'll have to retrieve it using the name, because the Python variable will be overridden. So we'll have to use one of the cumbersome kind of notations of TensorFlow, TF, get the default graph, so get the graph, and get the tensor by name, and then use that name :0, :1, :2, et cetera. So it's much better to avoid that. And there's one way to do that quite easily, which is just to use classes, function definitions, and methods which isolate the scope of the variables automatically. So I would recommend doing that, and we'll talk about that more later today. We've discussed almost all of the underlying data types, or data structures rather, so far, but there's still two more left. The first is that of a placeholder. And a placeholder is very similar to a tensor in that it does not store the value, but it does know the data type and at least partial shape information. The key difference is that a placeholder is not something that we want the code to compute for us. It's something that we want to pass to the graph to instruct it as to how it should act. So for instance, should it be training or should it be testing? If we have different courses or different computational graphs for those two cases, we may want to specify with a placeholder that we are training or we are not training. So we might have some Boolean placeholder. So this is always fed to the graph or given to the graph in the form of a feed dictionary, which is just a way, as it suggests, of feeding information into the graph, and it's in the form of a dictionary. So feed dictionary or feed dict is the way that TensorFlow uses this. And a simple example here, maybe we just want to shift some values. So we define a placeholder that will store some values. It does not know what those values are yet. We'll have to provide that to the graph. It defines a shift, which is just a constant valued 10, and we want to add that shift to the input. So we start a session, and we give it a feed dictionary, which is just a dictionary with label x, and values, in this case, 1, 2, 3. And the result can be computed again, yvals, just sesh.run. We give it the fetch, which is y, what we want to compute. And we also pass it information that is needed to compute that, in particular, the feed dictionary with the values of x. This will give us an error if we don't provide the feed dictionary, because it is not possible to compute the value of y without knowing what the values of x are. Okay, so we always need to feed in a feed dictionary so long as it's in the subgraph, or whenever it's in the subgraph of the computation that we're asking the session to compute. Okay, and so here we see, if I give it 1, 2, 3, add 10 to that, we get 11, 12, 13. So I glossed over something in the previous slide, which is why is the shape of that placeholder set to none? And this is very, very common. You'll see it quite a bit due to the prevalence of mini batches, or evaluating on multiple inputs at once. So it's much more computationally efficient. There's some stability benefits for doing this in terms of learning. And in particular, the first entry in the shape is typically reserved for the batch size. So it's how many entries we're going to evaluate at the same time. So in the previous example, we had 1, 2, and 3. We wanted to run this computation for all of those at once. And I didn't have to tell the placeholder that it had size 3. I just put none to let it know that that may change. What remains constant is that there is no extra dimension. So these are all scalars, 1, 2, and 3. So there is no additional shape dimension other than the none. It's just a list of scalars, basically. So a common or a typical example where you may have a different type of shape would be with images, so RGB images. You typically have some resolution, maybe 64 by 64, and then 3 channels, color channels, R, G, and B. And you may define a placeholder in this case with shape none for the batch size. It may change, but then 64, 64, and 3 for the height, width, and channel count. And so this is referred to as the NWHC format, N number of batches, height, width, and channels, which is typically the default. So the other dimensions are typically necessary to provide to the network, because the graph has to be fully determined, and it has to know what shapes of matrices or variables down the road need to be created in order to define the full graph. So in some cases, you don't need to give it the resolution, but in most cases, you do, unless you have something like a fully convolutional network. In some cases, it's OK to leave that out. But typically, none is reserved for the first to indicate a batch size, which may vary. So I mentioned, just in passing, variable. So what is a variable? These are the key component of the models that we're actually training. So in deep learning, we want to make a computational model, and we have parameters which we want to tune to get the best results or performance. These values are persistent in that they exist outside of the context of a run. They're always there, and they have some set value. So we typically have to initialize them. Maybe they all start at 0. Maybe we take some random initialization. And then throughout the course of basically training loops, we'll slightly adjust those. So our code will adjust according typically to an optimization algorithm to improve the performance of the model. And in particular, what these do is uniquely or completely specify the current state of the model. If you needed to make a prediction, all you need to have is the TensorFlow graph, the data flow, and the current values of your network parameters, your variables. So these are used to save models in what's referred to as checkpoints, which are stored in protocol buffers, which we'll discuss later. But it's a very minimalist way to save what you have basically accomplished after training. The variables, though, keep all of those values, the current state of the model. And just for completeness, I've given just an example of how you may use these variables. As we'll see later, in reality, most of the variable creation is handled automatically by TensorFlow now, using layers. But if we were to design some linear regression, for example, we may define a slope, an intercept, we'll have input and output placeholders, and define our prediction as add mx plus b. Okay, so multiply m by x, add the result by b, and then that gives us some prediction, and then we may define a loss function based on that. So how close is that prediction to the output? And so if we save the values of these variables, m and b, and we know the structure of the graph, multiply and then add, we can completely reproduce this model. Okay, so we don't need the code anymore per se. It's stored in a language-neutral format so that we can get the essence or the core of the trained model once we have those variables. So I've mentioned already that the graph concept can be a little bit confusing. I just want to briefly point out they have added TensorFlow's eager execution mode, which will do basically what you would expect a programming language to do for most of us, which is evaluate exactly when that line of code comes up. So it will define A in this case and B to be constants. We've enabled eager execution, so when we print the value S, the result of add A plus B, we actually see the value 3. So 3 is stored in that tensor. It's computed online. The benefits of eager execution lie mainly in debugging and also dynamic creation of graphs or kind of branching in your model. But it has some considerable disadvantages as well. It's usually better to use a graph. And the TFE module, or the tf.contrib eager module, aims to combine that eager execution usability with the efficiency or the advantages of working with computational graphs. And I just took from the API, there's a number of reasons why did they start using graphs in the first place. This eager execution is a relatively new introduction to TensorFlow. And the basic point is that it's more efficient, it's readily parallelizable, and it works well with distributed execution and advanced compilation techniques. So if you know exactly how your graph is set up, you know in advance exactly all of the data flow connections and all of the dependencies, you can easily distribute the computation across multiple cores. And in addition to that, portability, as I mentioned before, you can store these in a language-independent protocol buffer language or representation, and use this on a cellular phone which may not have Python installed. So you may write this very lightweight model, but if you have to install Python and all of the libraries and dependencies of TensorFlow, it's not lightweight anymore. So instead, we can run it with the low latency C++, which is much more likely to be installed on these devices already. Okay, so I want to now go into some of the kind of newer features that make TensorFlow much more usable than it used to be. And one of those is the TensorFlow layers module. This basically automates some of the standard building blocks of deep neural network design. So things like activation functions, bias terms, weight regularization, and any constraints can be incorporated into these in a relatively seamless fashion. And so some of the, but not all of the commonly used layers are dense convolutional layers, dropout, pooling layers, and batch normalization. And these are all implemented for us. So we really have very little programming we have to do in terms of creating variables, creating weight matrices. This is all automated, and it's very convenient. And so you can see the full list here on the API, and also there are recurrent neural network cells like LSTM cells and GRU cells on the contrib layers.rnn. So how do we design a network if we're trying to make a neural network? We'll go into more of the theory of this tomorrow when we go to the talk Understanding Neural Networks. But for our purposes, we just want to define a dense neural network, and we can do this in very few lines. We define our input and output placeholders. We give them a shape, which is none for the batch size and 1 for the remaining dimension. These will just be kind of single valued vectors. And we define a dense network. It takes an input and maybe a name to assign it. And we just stack tf.layers.dense on top of itself 3 times. First, we have an input, which is x, the original input, and then we transform that hidden output, h, twice more, and end up with a resulting layer of 1. So we have kind of 10 units, and then 1, which matches the desired output shape of y. And so we need this none, 1 for this to work, because in the layers module, they always assume you're doing things in batches. So it's just one thing to point out. Also, we'll mention later, activation function makes sure at the end you take into consideration what you want to predict. And if you have negative values, for instance, using a rectified linear function, which only produces positive values, is likely to fail. So just a few little points to take into consideration. And these layers are very helpful also because they're so modular. You can really just use them in any way you want. And so in this case, I've just added dropout. Maybe you increase your dense layers to have 100 hidden units, but maybe that you might be worried about overfitting, so you add in dropout with a rate equal to 0.1. So this will just drop out nodes as we're training. But there's an issue here, which is in this attribute here, or this argument, training equals true, we don't want it always to be true. If we go to test and we start removing or dropping these units, then we're going to be getting a stochastic or a random prediction. It's going to vary depending on which units you drop. So in most cases, we want a deterministic prediction, just a constant prediction. And this can be accomplished by using a placeholder. And this is actually a much more natural use of placeholder. We'll see later it's more efficient to use a different API for feeding in data. But the training can be fed in as a placeholder, in this case a Boolean placeholder, and we can set the training argument of this dense network to be either true or false for any given session. So are we training, are we not training? Again, that's something we know and we want to inform the network of. And another concept which is very important is defining custom arguments or default parameters for layers. And this is more important, especially as you start to try to model different research papers that come out. They won't be automatically given to us by TensorFlow likely. We have to write them ourselves. But it's very easy just to combine some of the existing layers in a new function. So maybe I want to define dense that has some default initialization. So we have these initializers for our weights and uses a dropout by default. I can always change this so that it doesn't use dropout. I still have control, but it's just a simplifying measure for writing your code. I can just say dense x10, dense x10, and repeat, and not have to worry about specifying these parameters each time. So it's a nice, convenient way to simplify your code a little bit. So TensorFlow also has a number of predefined loss functions. So again, these loss functions will be used basically to guide our training process. We want to minimize the loss to improve the performance. And some common examples are the mean squared error for regression and softmax cross entropy for classification. And custom loss functions can also be defined, but as we mentioned earlier, it's important to use TensorFlow operations just to be on the safe side. Just to make sure that the gradients are computed correctly so that the back propagation of the flow of gradients is not basically damaged by a missing gradient in one of your operations. And also these tend to need to be reduced. So you'll see these operations like reduce sum or reduce mean. And what that means is that it will collapse the dimension. It will take the sum across all the dimensions and return just basically batch size scalar shaped value, which corresponds to the loss for that specific example. So in addition to a loss function, you need an optimization algorithm. And again, there are a number of predefined optimization algorithms. They also list the original papers with the parameters, so you can go through and see kind of what these beta 1, beta 2 parameters mean, for example, in the atom optimizer, and get a sense for what good defaults are. They typically have good defaults for the most of these, but there are some which you really do need to tune it to your data set, especially the learning rate. So in this case, or once you have selected the optimization algorithm that you wish to use, you need to define an operation for carrying out that optimization step. And this is done most frequently using just the dot minimize method. So we tell it, basically give it its parameters. 0.001 is the learning rate in this case, and dot minimize tells it to compute the gradients and to apply the gradients in a direction which minimizes the loss which we've defined. So we provide it some loss. If you want to do something a little bit more complicated, such as clip the gradients, if you don't want to have gradients that are too large, adversely affect the training process, you can also do this manually by a series of just compute the gradients with respect to the loss, then clip by norm, so by the L2 norm, for example, and then apply the gradients. So minimize is just it's a shorthand for computing and applying the gradients. Now, one of the things that I briefly mentioned in the custom or default arguments slide was variable initialization. So there is a default initializer, which is this given here from this paper, Understanding the Difficulty of Training Deep Feed-Forward Neural Networks. But we can also assign our own, so something like a truncated normal or just a standard normal. And that will tell the graph what should be used to create or initialize those first values of the variables. After that, they'll be changed by the optimization algorithm, but we need some initialization first. And in particular, those operations have to be called. So again, going back to this graph concept, we need to actually execute those initialization operations. And this is done by the global variables initializer, typically just referred to as like a init, and we just run that at the start. So that will initialize all of our variables for us. But there is a somewhat standard initializer set by default as well. Okay, and so putting this together just briefly, so we define our prediction using, from the previous slide, we had dense network, for example. We put our loss function in the graph, so this will be the mean squared error between our y and our prediction. We specify the optimization operation, which is just to minimize the loss using the atom optimizer. and we initialize our variables by defining a init op and then running that init op. And now we can loop through, so I'll just make artificial data, and this will learn basically the values of pi on roughly the interval minus pi halves to pi halves. And again, we, in this case, are feeding in both the x values and the y values because we want to run the optimizer, which depends on both. So we need to know the y values to compute the loss, and we need the x values to make our predictions, which are required by the loss. So we'll compute all of this, and you'll see this actually converges quite well. Just one more look at the tensor board graph, the kind of TensorFlow's visualization tool. We see that the input values are passed basically to two dense layers. Those are converted to prediction. We take the mean squared error. All of those variable values are passed to the atom optimizer, along with some parameters, these beta 1 and beta 2, and then it computes and applies. So this is just a little bit more realistic data flow graph. One additional note that I want to mention, and again, these are just things that are very easy to miss, so I want to highlight. When you are using batch normalization, which we'll discuss more tomorrow when we go into the theory, but if you're using it, it's not sufficient to just include tf.layers.batch normalization in your graph. You need to tell your optimization algorithm that you are using batch normalization by assigning these control dependencies and these update ops. So the update ops will basically store and control the batch normalization during training. And it's also important that it knows when it's training and when it's not, so that it acts appropriately as defined in the original paper. So this is just another key. If you just put those into the graph, the tf.layers.batch normalization, it will not apply batch normalization, or will not do it correctly. OK, so now I want to move on with just the last bit of this talk to implementation details. And so I'll go through this a little bit quickly because this is actually still not the best way. We'll talk about that in the second half. But I just wanted to point out that feeding the data into your network is the least efficient, according to TensorFlow. I don't know. There's probably some less efficient ways, but it's definitely not the recommended way to feed data into your graph. Instead, what we'll use is a dedicated module, tf.data. Okay, so placeholders are more for, is it training, things like that, things that you just want to tell it to switch something on or off, very small pieces of information. When you work with larger data sets, you want to basically avoid having Python move things around and instead work with the C++ backend of TensorFlow. So in the past, we had this queue runner, which is very difficult to set up. It was not easy, but luckily they've worked quite hard, I imagine, to really streamline the process of creating these queues into the tf.data API. And the two basic components of the tf.data API are the data set and the iterator, which are quite natural, I think, after you get used to them. A data set basically contains a list of training examples. So an example is, for instance, my input and my output. That's one example, and I want to train with many of these examples and combine them into a data set. And I guess the key to why we need data sets in this tf.data API is that we're going to provide streamlined approaches to batching, transforming, pre-processing, and shuffling the data. So there's these things that are just recommended that we do. And in this setup, we can basically do all of that with a few lines of code. Once we have the data set, the only thing that remains is creating an iterator to actually get the elements or the batches from the data set. So again, it's kind of that graph session mix. The data set gives us the kind of graph component, but to actually retrieve those values, we need to define an iterator and run that iterator with, in particular, the get next. So that will get the next element, or if we have put it into batches, it will get the next batch. And so here is an example usage. It looks a little bit long, but if you look at what we're actually doing, it's quite a number of different steps that would take a lot longer if we were writing this out manually. So what we do here is we create our data from tensor slices. This is the not so efficient approach, or less efficient, but then we can repeat this data set 5 times if we want to train for 5 epochs, for instance, and then shuffle that data with a random buffer of 2,500 examples. So this is basically an indicator of how random the shuffling is. And for large data sets, you may need to keep that small, like 2,500. If you have something like MNIST, you may be able to just get away with increasing it to the full size of your data set. But this will only basically shuffle in groups of like 2,500. And then we can put that into batches by specifying a batch size, and make one-shot iterator just automatically creates that iterator. And so now we can say get next in the TensorFlow graph and get basically these batches of shuffled and repeated elements.
I have a question.
Yes.
So so basically, like X data is the set of all the. Suppose I have a data set of images.
Yes.
X data is the combined NumPy array of all the images in the data set.
Yes, it would be the first dimension should be the number of examples. So maybe if it was images, maybe it would be you had 100,000 images and they're 64 by 64. So you would have an array of 100,000 by 64 by 64. And then maybe your outputs is just one value. It'd be 100,000 by 1. So they can be different, but that first index should specify the number of examples that are available.
If the NumPy array is too big and it doesn't, my RAM runs out of memory.
Yes, great question. So that's what I mentioned about efficiency. This is not the ideal approach. The TF records will be the solution to that, or for the most part. And we'll get into that in the second part. But yes, we'll save these into more concise files that store the data set, and then we can retrieve bits and pieces of it instead of loading it all at once. Yeah, so that's exactly one of the downfalls of just the first part. So everything else will stay the same, but the from tensor slices, it's quick, convenient, but not necessarily the most efficient approach. And now, so how do we use these? It's very easy. So for example, if my data set consists of elements with inputs x, outputs y, I can just say my x batch and my y batch are the outputs of the iterator.getNext. And now anytime I call loss, it will know that it needs to compute the prediction. And in order to compute the prediction, it needs the x batch, so it will run the iterator.getNext. So you just put this in, and it will automatically retrieve the next batch, these shuffled batches, and compute just as before. So we don't have to do anything in the sesh.run differently. We just place the iterator in the graph. So it's quite easy to work with once you get the hang of it. And so I won't go through this right now. We'll go through it in the second half. But the more scalable approach, as we were mentioning, is using these tf.records files, which allow us to basically work more efficiently with larger data sets and are helpful for distributed computation. So to wrap things up, I want to talk about just the tensor board, the visualization that I showed you, and then also just a quick word on the use of classes. So in order to visualize your graph or your loss, you can get these nice loss plots. You need to save what's referred to as a summary. And typically, these are scalar summaries. There's other types of summaries as well, but a scalar summary is useful, for instance, to track the loss. And to save a summary, it's relatively straightforward. We just define a summary operation by tf summary scalar, give it a name, and identify the Python variable representing the symbolic tensor that we want to track, so in this case, loss. And then we also define, in most cases, may not strictly be necessary here, but a merged summary operation. So in most cases, we have more than one value that we're tracking. So this will merge all of those values, all of those summaries, into one operation, which we can call just by running sesh.run, as pointed out here, So we want to optimize, but we also want to get a summary. And in order to save this, so that will compute the summary, but we want to actually write this to a file, we first get the graph, so just get the default graph. It may do this automatically. I'm not 100% sure, but in this case, this will work. If you get the default graph, pass that to the file writer, tf.summary file writer, give that a name, so your logs, or the name of the directory you want to save it into, in this case logs, and then add a summary every step in this case, or you can do every 10 steps or so on. But we just add the summary, and then at the end it will close that and give us a file which we can access. And in general, you can actually access multiple summary files, and what you really just need to give it is the log directory. And we'll see when we get to validation why you would maybe do this. But what we can run from the command line is just tensorboard logdir for log directory, and then logs. So that this is coming from the case where I've specified to save it in a folder or directory called logs. And now you can go to your localhost port 6006, or you can try some other things if it doesn't work. It should work. And it actually should, in the newest TensorBoard, tell you where to go. It'll say, please go here. And you can navigate it in a web browser, which makes it nice and kind of convenient. And also, it's interactive. You can scroll around. It's just inside of your web browser. And you can visualize things such as the loss. So here's the training loss, for instance, on something that one of the really basic models. And there's some other options that you can see. Also, looking here in the bar at the top, there's scalars, those are your summaries, and then also the graphs, which are the graphs that I've been showing previously in the presentation. So it's nice for visualizing. These can also be cleaned up by using name scopes. I didn't include that just because it's a little bit verbose for slides, but they are helpful. And then one other thing, I'll kind of, for the sake of time, skip over a little bit of the details, but I'll post these slides so that you have access to them. They can also be used for identifying computational bottlenecks. So it's a little bit more involved in the coding, but we can see basically graphically where, and it's colored or shaded in this kind of dark red, our computation time is the longest. So we see it's not really this first one that's giving us the problem, it's these second two. In this example, it's not very interesting, but if you have a very large graph, this can definitely be helpful in identifying a bottleneck, one layer that may be taking up half the time of your model. So very helpful. And I guess I'll kind of just go through this briefly, probably in the next 5 minutes, and then we'll take a 10-minute break. But the way that I would recommend defining these models is in terms of classes. For one reason, again, there's the variable scope issue and overwriting names, and if you just happen to use X again or something like that, you can run into problems. But also because it's a natural case of using these class definitions. Our models do have certain attributes and methods naturally, which we can think of. For example, we have our graph, we have our session, we have a data set, a global step, which we'll get into in the next half of the talk, maybe something to save, and some training hyperparameters. These are all properties of our model, our current model. And the methods that are natural are maybe to give it a session. What session is it working with? Again, we'll go over this in more detail later. Maybe to build the model, construct the graph, make a prediction, train it, evaluate it on some test data set. These are all natural things that we want our model to be able to do, and it makes sense to define it as a class so that we can just call these in a kind of natural way. So this is a little bit of just an overview of how classes work in Python. They're not 100% necessary to use this format, but it does have this @property wrapper or decoration, which allows you to define basically a getter and a setter for these attributes. You can also define them directly, but it may be worthwhile to use these if you want to kind of follow the proper Python coding style. And methods are defined basically as you would expect within the class definition. And the only technical detail is just to add self at the beginning, and this just tells it to provide the current instance of the class to the method, so it knows what it's working on. So you just always include self in kind of a hand-wavy way. That's really the most you need to know. And then self dot just refers to different values or properties or methods. So I think for the most part, Python classes will not be the difficulty. It will most likely be the TensorFlow coding that can give you more problems. But in terms of creating classes, just one more, I guess, slide on the basics. We inherit from object here just for Python 2 compatibility. You don't necessarily need to do that. And the init method is used to start or initialize the instance of a class when it's called. So we just, in this case, define obj equals my class 1.0. That 1.0 is taken as a parameter. It's used to initialize. And then we can call methods and print out the values of those. OK, and so really the main keys are the init method can be used to kind of get your model started. It can check for training data sets on the file system, make sure that everything's in place before you start training, because it can be difficult to go through the TensorFlow error messages. So you may want to perform checks of your own prior to those error messages to realize, oh, the data is just not there. TensorFlow may give you some less helpful information. So I would recommend making some of these checks. The init method is good for that. Build model is just basically construct the graph, get things set up. This could, for instance, be called by the init method. And then train, predict, and evaluate. This is following the API for what TensorFlow refers to as estimators. My examples are not strictly speaking estimators, but they follow the same principle. Basically, you should define a train method, which trains the model given an input function. So you tell maybe the iterator for your data set. And then a predict method for making predictions, and an evaluation method or evaluate method for evaluating your trained model in terms of your specified loss function. And so I think for the most part, that is all I wanted to say for the first half of this talk. Here's just an example of putting that all together. I think it should be relatively straightforward. I guess the one last key is that we can use this kind of fancy ending. If the name of the current program is main, then it calls the main program. This avoids that whole program or code above being called if you're just importing this in another file. So if you're running this directly from the command line, it will assign the name main, and then it will execute this. And so this is just an example kind of workflow that you would put after you defined the object and the classes. And we'll get much more into this later. Just two things I wanted to point out. I have some examples, some kind of basic examples on GitHub, some very simple ones just to get started, and you can run them and see how they work and see the plots they produce. And also there's some rough explanations on my math website. Still much more to add to that. But you can take a look at that if you want more explanations, a little bit simpler explanations than I've given here in these kind of more technical slides.